The brief introduction about our company also, I think people might have not given. So basically our company name is Metro India Limited. Basically ours is a Swiss-based company. Headquarters is in Switzerland. Okay. Metro is known for their analytical range of instruments. Basically like starts with high-end pH meters, conductivity meters, ion meters, and then we have automatic titrators because Metro is known for their automatic titrators, and then we have Fisher titrators for finding this moisture content in different types of samples, and then we have ion chromatography, which is basically like chromatography technique used for this detection of anions and cations to very low level PPT level of detections, and then we have instrument called polarography, basically for heavy metals analysis like zinc, lead, copper, cadmium, and this kind of heavy metals also. It's basically kind of electrochemistry instrument which is used for quantification analysis actually in industries. So we have that instrument also. That is our analytical range. And other than that, in the spectroscopy side, we have this Raman spectrophotometer, both handheld and portable systems. Okay. And then we have NIR systems, which are used in different industries. And then this electrochemistry range, okay, which is like depending on the current and voltage range, we have like different models, okay, and also like depending on number of channels you want, okay. So we have single channel and multi-channel systems. So and then we have something like a water purification system from a company called Elga. It's a UK based company, because you in every analytical lab they need like high pure, ultra pure kind of water system. So our systems can produce 18.2 megohm, that is the quality of water they will be expecting, which practically should not have any minerals or any this one, okay, free from any organic this one. So TOC level should be also very minimal. So we have from tap water, that kind of systems can produce this ultra pure water. Okay. So we have that range as well. This is our product range. And in India, we have sales and service operations, and we have 13 branches all over India, and we are almost close to 200 people in sales and service put together. Okay, we have, it's a strange company, like 40 people in sales and almost 150 people in service. So we have that kind of ratio. Like literally, we get 70 to 80% of the business from our service itself. So that's why like the ratio is like that. It's very strange. And like many people will ask. Normally, like the ratio will be like this. Sales people will be 3, and then service will be 1. But in our case, it's totally different. Okay. So this experiment, if you compare all the other things, it's one of the simplest experiment we created, because sir said like there are some students like who has never touched this electrochemistry, so just give some introduction. So what we are going to see here is simple cyclic voltammetry technique. So with free Ferro systems, because for any electrochemist to start, this is the system they start with, because with this experiment we can also confirm the system is working perfectly fine. Okay, and basically this CV is used for finding this you all know like redox potential of the particular reaction. Okay, so plus the other things also, whether the reaction is reversible or reversible, all those things we can do with this. Okay, maybe then I'll just get it. This instrument, the model number is, we call it as 302N Autolab, means like 30 volt of compliance voltage, and then 2 amps of current. This is the range. It's a compliance voltage is slightly different from applied voltage. It's like applied voltage is the speed of the car, but this compliance is something like power of the car. Okay. For example, like if the solution resistance is very high, to apply the 10 volt, you need to give more push, so that the potential difference between these two electrodes will be plus or minus 10. So there people always will have that confusion, like what is that compliance voltage? Compliance voltage is that power up to which this can push that, so that it ensures that the potential difference between this uh, working and reference electrode is 10 volt. Okay. So I'll a small presentation this time. So this is the experiment we have planned with this system, like cyclic voltammetry. Okay. So what is cyclic voltammetry? Like it's an electrochemical technique used to study the redox properties of chemical species by applying a potential sweep to a working electrode and measuring the resulting current. Okay. So this instrument also, like all the other instruments, you can do all the DC techniques as well as impedance measurements. Okay. So if you want to do LSV, like linear sweep, cyclic voltammetry or chrono methods, you name the techniques like pulse amperometry, all those things, everything can be done with this instrument. So what are the steps involved in cyclic voltammetry? Basically it's a potential sweep. Okay, maybe for some people it may be primitive, but we have designed it like so that for the beginners also. Okay. So it's a potential sweep what we will be doing to the working electrode, and generally like we start with one particular voltage, for example 0, and we'll go towards that first vertex which is just after this actual redox potential of the system, and then we'll come back to the negative, and then again go back to 0. So that's why it's cyclic voltammeter, like we are just doing a cycle. Okay. And then we do the current measurement. It's a potential static mode, so we are controlling the potential and measuring the current. Okay. And then the voltammogram is the what we'll be getting, like between this current versus potential. So it's a simple information, like what all the information we'll be getting from this CV, cyclic voltammetry. So one is, as I told you, this redox potential. Okay. See what we have here is a ferro system, we call it as basically potassium ferricyanate. Okay, in 3 molar case we have prepared. Okay. So we know this redox potential of this particular system is somewhere close to 0.35 volt. Okay. So when you run the CV, the instrument should detect that peak somewhere in the range of 0.35 volt. Then we can say like everything is fine with the system. So people normally, like if they find some issues with measurements and other things, to confirm whether everything is working fine, they just run this test and then it will confirm that okay fine, like my system is working all right. Okay. So that's why this test is relatively, like irrespective of the kind of research they do, like they do this one, okay, just to check the performance of the system. Okay. And okay, so one thing is with this experiment they can find redox potential of different reactions. That is one. Okay. Second is it will also tell you whether the reaction is reversible or irreversible. So we do forward sweep as well as reverse sweep. Okay. So if it is a reversible reaction, like both the sides will be getting proper peak and will be keep on continuing. If it is irreversible, like we can see that peak height coming down, or in the reverse direction nothing will happen. So depending on that type of reactions, we'll be getting the different peak shapes. Okay. And also it will give you information about this electron transfer, 1 electron or 2 electron, all this transfer information also we can get. And then reaction mechanism, again if there are any intermediates coming up in the reaction, so that information also we will get from the shape of the curve. So that is also possible with this CV. Okay. Also quantitative, one of the major application, like practical, they say everybody is telling this applied research. So this is one of the thing people can do, like we can do quantification of the components or concentrations we can find with this CV technique. We all know this glucose meter, whatever, for measuring the sugar. Basically it's like based on this technique only, like they do the sweep and then find out that peak height. That height is directly proportional to the concentration of the sugar in the blood. Okay. For example, like if the sugar level is 100, if the current is, the peak height is 100 microns, for example, I'm telling. If it is 200, it is 200 microns. So of course we need to do this calibration and many other things, but basically this is the kind of technique they use for quantitative analysis. Okay. So this is like about this reaction, whatever we are going to see here. Like, so ferricyanide will reduce and then will become ferrocyanide, and then in the oxidation side, like it will become ferricyanide. Okay. So of course, like anybody is aware of like why this three electrode system. In any measurement system, like we will be having two electrodes. Like one is working electrode, we say, another one we say reference electrode. But why these three electrodes? No, no, we can do from the same distance. We can, no, 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 we can do that. But since because of this, yes, you are correct. Okay. We will be having a lot of disturbance when we do that measurement through the same electrode. So that is why, like what they generally do is in three electrode system, they apply the potential between working electrode and reference electrode. Okay. But here the resistance is very high in between. Okay. So what do they do is like measurement of current they will do between working electrode and counter electrode. Counter electrode is generally simple platinum wire. Okay. So that is why like in most of the electrochemical applications you will see this three electrode setup. See that setup? No, no. Okay. So it's a prerequisites for this experiment. What we have done is we have prepared a solution of potassium ferricyanide, 5 millimolar they have mentioned, but we have taken 10 millimolar just to have better curve shape and other things. In zero point 0.1 molar KCl they are given, but we have taken 3 molar KCl, which is more stable. Okay. So then we have set up this CV experiment with three electrode system. You could see like three electrodes. So we have this working electrode is GC, glassy carbon, and reference electrode, you all know AgHCl reference electrode, and then counter electrode is a platinum wire electrode. So this is the setup. And what they have given is the range is like you start from 0 and go to 0.6 on the positive side and then minus 0.4 on the negative side, so that this 0.35 comes in between these two. So that is the range they have suggested. So this setup we will do in the software. Okay. Again, this there are a few factors which will be affecting this shape of the curve. Okay. Basically, the scan rate. Okay. If you increase the scan rate, that also will change the peak current and separation and many other things. If you do it slowly, suppose your reaction is very slow, and you do very fast scan, reaction like could not follow that change of voltage, so the shape and other things will be bad, so you have to adjust it accordingly. Slow the rate, normally that response will be better. Okay. And also it depends on the electrode material whatever you are using. Suppose instead of classic carbon use different electrode, then also like there may be a change in the shape and other things. Of course also this solution conditions, for example, like if you had instead of a 0.1 molar KCl, if you are using like kind of acids, for example, like see they given some example, like if you are using HCl, this redox potential will shift to 0.56 from 0.35. So that is because like the change in the pH also plays a major role in this redox potential. So if you use even higher concentration of HCl, it will go to 0.71. It will just go further. Okay, so all these things are important when you are doing this kind of studies. Okay, so this is about this. Okay, we'll just get into the software. Okay, this is So now just I open the software. So it says the device is ready for use. That means every connection is fine. Okay. See here we have like kind of library in which like all the default procedures like in as I mentioned in the beginning we could do all DC measurements as well as this impedance measurements. In DC itself we have very like multiple techniques. For example like cyclic voltammetry like with the potentiostatic we have, cyclic voltammetry galvanostatic we have. So like this like cyclic voltammetry linear scan. So we have different types of CV techniques for different kind of applications. So all these kind of techniques we have some kind of reference methods. So if somebody is not aware of like what to do, you can just open this demo methods and then you modify the parameters according to your application and start the running. Okay. So right now I'm going to take a cyclic voltammogram potentiostatic method. So just it's a default method which is there in the system. Okay. So here it talks about like how the method process goes. Okay. So first what it will do is like it will not apply, it will apply just 0 volt and then switch on this cell. That means this system and the electrode will get connected. Then it will wait for some 5 seconds. After that it will start this cyclic voltammetry. Okay. So these are the parameters of cyclic voltammetry. So what is given here is it will start with the start potential of 0 and then go to the upper potential of 1 volt. Yeah. And then it will come back to -1 and then again it will go back to stop potential of 0. So it's like a cyclic voltammeter, right? Starts from 0, goes to positive and then comes to negative, then again go back to 0. Okay. So and then the number of scans, how many times you want to scan. People sometimes do multiple scans, as I mentioned, like people who are interested in reversible reactions or irreversible reactions, they do multiple times and then see whether it is exactly happening or not. Okay. Scan rate is like it's a 0.1 volt per second. It's a default they are given. So as I mentioned, this also plays a major role. Like if you give very fast scanning, the reactions will be incomplete and you will not get proper shape. So you have to optimize in every method what is the voltage scan you are feeding. Okay. So just after entering all these parameters, you can start like, so now everything is connected and method is set. So you can just click this button to run that experiment. Anyway, after this I will leave the system to you. People also can vary things and play. So this is the kind of voltammogram we are getting. Like it started from 0 and then will go up to 1. Yeah, goes to -1. This can go up to even femtoamps. It can go femtoamps, like it's nanoamps, picoamps, and femtoamps. It can. That is the level of sensitivity. Nanoamps range, people will work in nanoamps range. Yeah. This can be used for higher current. This can measure other side. It can go up to 2 amps. So this system is like it's a complete range. There are systems where like the current range will be 100 milliamps or maybe it will be 101 microamps, something like that. So that time it may overflow. But sensors normally, if it is going above, there is something else wrong actually. Yeah, micro to milliamps you are measuring. But in sensor, if it is going above that, I think there is something else. Normally it will be in that range only, micro to nano actually. Yeah, correct. So this is the graph, like whatever you got, like, but this is also not bad. It has come all right. I tell you, if you want to see the peak, see we are interested in redox potential. Okay, so I'll just select peak search, and it will tell you like it has identified 3 peaks. But okay, this is peak 1 and 2 are our important. See here 0.36 is what we got as peak potential. That's redox potential. So as I told, it should be close to 0.35. Okay. So this is fine because we have altered a little bit of concentration and other things to get better peak. But if you exactly prepare that and see, it will be exactly matching. So that is to confirm like everything is working fine. Okay. Then after that, people will set up their own systems like and study like what is the redox potential, how the see this is like almost I would say it's reversible, but we'll just change the range. Now we are given huge range, so it's not looking nice. So what you can do is like so I'll go from zero point 0.7 whatever they were talking right and to 0.20. Okay. So now we'll see you can see the change in the shape. See, generally, like plus or minus, you should be knowing this system can scan from like -10 to +10. But at least you should be having some Faraday. Otherwise, you just do complete scan and then choose the range. Yeah, yeah, yeah. Normally, like plus or minus one people stood, or maybe plus or minus two, depending on like fairly there will be some idea, but some papers will be referring to. If you're not having any idea, just choose that wide range and just see what it is happening. Yeah, yeah, correct, correct. So I think electrochemist will be having some idea definitely. Sometimes selecting wrong range also will burn the electrodes and you may end up losing the electrodes also. Yeah, slowly, slowly. Because morning there are small loose connection in the electrode, so it changed the color to blue. And something went wrong. So, okay. So now if you see like this is relatively like only we have closed this range. Okay. And still if you want to optimize it, you can still do it with, for example, scan rate. Like we have kept on the higher side. If you reduce the scan rate a little bit on the 0.1, sorry, things will be slightly better, but it will be slow. But, start with that. Yeah, yeah, yeah. That's what it all comes with from experience. Yeah. See, that's why, like, if you see the default method, no, they're given +1 to -1. You can start with that. Some people are really expert in selecting that range, speed, and everything, so they will get nice graph so that we can. But okay, of course, it's not only that, also the kind of system we are using that also decide this shape. Nothing will happen. No, it's okay. Nothing will happen. some people they do it for hours together. They use very slow scan rate and do that. So, I think in organic they do it slowly. I guess the actual shape speed is very less. So like if you cut it somewhere in the zero, like maybe you may get better shape. This side also if you cut. So that's how they play around with that to get better in this one. So one experiment, maybe if you want to do multiple scans, as I mentioned, like you just increase this number of scans to 5, maybe I'll increase the speed to 0.05. Which one? Yeah. No, no, not necessarily. Like, all depends on like your sample. Some people say you should do that reaction in inert conditions. So they pass nitrogen gas. See, if you see, this reaction is almost reversible. So you can see like the peak shape is almost like it will be, even if you do multiple sweeps, it will be almost similar. Okay. Otherwise, like only the forward will be, the reverse will be completely flat. If it is irreversible. So this will become better actually. So this is actually unnecessary range actually. So you can choose between like 0 to 0.6 should be the range. You will get nice graph actually. Because that are like just unnecessary range actually. It's not required actually. Okay. So now this is over. See, this is 5 scans, right? We have this 3D kind of images also. If you want, you can just see like, so and just if you want to compare, so that is also possible. Like all the 5 scans you can analyze, and if you want to store like individually, also you can store individual scans. Okay, so that's all possible with this. Okay. No, no, see, at least, the safe range will be like from the peak potential or this redox potential, you just give plus or minus zero point 0.3 this side and that side. So that will be like, no, 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 it is not that. No, no. We are just trying to avoid that other things. Because of that, that shape will be little bit looking odd. It will not affect. Okay, you go to, no, no, no. Just to get better window and save time, we are doing that actually. It will not enhance or it will not do anything. That may be because of the wave shape actually. That is because of the wave shape you are applying, not because of this range. Yeah, see again that different shapes will have different response actually. No, no, you can't say because it depends on the reaction type also. DP I have not programmed it here. Maybe DP no. I will, DP there is a method, but it can run. Okay, it's last experiment, so no problem. Set பண்ணுங்க, just set, you can set the range. இங்க இருக்கு. Okay, வந்துச்சு டிபி வந்துச்சு. But DP, you should do this at a position. Many things are there. Okay, yeah, fine. Usually differential pulse கொடுத்துறாங்க. Okay, no, no, I'll just do that. We'll start with start potential of forward மட்டும் கொடு. Okay, fine. Start with 0.7 கொடுத்துருமா? Okay, step modular amplitude. Okay, fine. I'll just give that. Anyway, you can run all the techniques. It's not that. வந்துடும் வந்துடும். So anyway, that's all. You can run and see whatever you want to see. It's a simple save system. Anyway, at least it's coming all right. No, it's not that bad, right? Okay. To be honest, you people are more expert on this because I'm not electrochemist, just I can. I know where is what. Okay. So that's all from my side. Maybe. How to calculate? Surface area. This calculation, I think I have to contact Manikandan only. You know, I used this system 15 years before. Since they wanted one more hand, so I just joined them. Okay. So I know almost. When we were handling it, maybe Auto Lab, there was a software called a GPS. Actually, that was different software altogether. They changed everything. Now it is software called Nova. So, which I learned it from him sometime back just to demonstrate. Yeah. Yeah. So if anybody is new to the software, maybe you can just play around with that. Nothing will happen. So you keep the simple system so that people can. Huh? It's all, as I tell you, IBM secret is like they were ex-employees of Auto Lab. They went out and started almost many things will be similar. There are two people from R&D. They went out and started the CVM actually. So both are from Netherlands, right? IBM also from Netherlands. Yeah, yeah, yeah. Yeah, we also have something called as micro auto lab, we call it as. It's a small system. The current and voltage range is less actually, plus or minus 5 volt or something like that. Yeah, yeah, like that. Correct. Fine. So that's all from my side. Any questions? And we have a little bit of modern features like suppose the like in between steps you want to get some kind of email or something. For example, people keep it for like hours together in waiting and some kind of things in between steps. If they want their attention, they can just incorporate that steps. So it will send a mail, and then you can just come and then go to the next step. Like so, in between steps, you can add some comments. Like, and if you want to loop things, there is a provision. If you want to make some noise, there are provisions. So there are so few more features they have incorporated in the new software. Okay. Easy to program. Earlier we used to program like it was like a computer programming only. Like literally you have to remember that code words everything. So now it is only the picture. Like you just move the pictures, then it's ready. Method is ready. Fine. In Bangalore, see, IASC majority of the departments they're having. Somebody was mentioning Dr. Sampath, IPC department. SSCU, solid state and structural chemistry. IAS itself, we may be having some 10 15 systems, we should be having. SICRI, we have more than 50 systems, I think. Yeah, IIT, Mumbai. Like all over India, maybe like it should be more than 1,000, like easily. Every year we sell around 100, 150 systems we sell. So almost 20 years we are selling, then you can see the numbers like we have huge number in place. We have different models also, like as I mentioned, like this is a little bit of, I would say 302 is our top end model, which is like almost people they will be willing to get funds for this and buy it because it's a little bit on the higher side actually pricing. It's almost close to 30 lakhs, 25 to 30 lakhs it will. Hmm? Which one? Yeah, this is stand. Yeah, it's not a problem. That is actually made in here only. Like stands and all, if you import from them, like it's too expensive. Yeah, electrodes we have locally made electrodes also. We have imported electrodes also. Depends like which electrode you want. Like GC, that's what I can say, from 5,000 to 50,000 also we have, like, depending on the brand and the quality of the electrode. Same, like platinum also in that range only, because depending on the manufacturer it varies actually. Simple cell setup, okay, you can get it for locally made, something like uh, 15,000 you can get it actually. We need to give some decent one, like you can get it. An imported one comes around 1 lakh actually. The full setup, 3 electrodes and all this holder, everything, yeah. Well, depends on like what kind of quality you are looking for. So, there are no more questions, then we can close this also. We can start. Yeah, thank you. Good name?
Swaminarayan.
Sominarayan. Sominarayan.
Swaminarayan.
Okay, fine. That's fine. ಈ ಕಾಲೇಜಲ್ಲಿ ಹೆಂಗೆ
Nitya Meenakshi.
நித்திய மீனாட்சி காலையில் மார்னிங் சொன்னீங்க இல்லையா? ஓகே, பெங்களூர் ஆஃபீஸ் மீட் பண்ண சொல்கிறேன்.